Let's continue working on the workflow for doing the checkerboard test using the ambient noise data that we have been talking about in the previous video. So in the previous video we talked about how to download and install, compile and install all the source codes, and and also how to actually um, create the box for the velocity model and also the box for running the wave propagation simulations using SW4, and also uh, how to actually create the R file. It's a specific binary sort of file format for storing velocity models, for storing three-dimensional velocity models. That's going to be used. It's going to be read by SW4, right? Um, so now we've got the velocity model, we've got the boxes, right? We've got the simulation box and uh, the velocity model box. Now let's keep working on the setup of forward simulations. So the next step is gonna we'll have to generate the input files that's gonna be read by SW4. In order to actually generate those input files, we will need um, a list of the sources and the receivers, right? So last time I was showing you uh, the the parameter control file for the entire inverter. One of the so we've got the box VM, that's the velocity model box. That's the prefix for the velocity model box, right? And then it's actually two output files. One is box underscore r dot UTM. That's gonna store the UTM coordinates of the four corners, and then box that's and then underscore the box r dot ALL. That's gonna be the azimuth and the longitude, latitude of the origin of the box, and the size of the boxes, length and width of the boxes, and of the box, and um, yeah, and the projection string basically. And then we need a list of the sources and the receivers, and we also need a source time function, right? So in principle, all those information could be different for different sources in the source receiver list, right? But if you specify the source time function and source type inside of the inversion, this particular control file, then it's going to apply the same source time function and source type to every source that's listed inside of this source list, right? But now let's look at the source list, right? The source list uh, is just a simple text file, so um, it doesn't have any kind of descriptions like with the AWP code, right? In AWP code, each of the sources is going to have a description about the grid location, the source type, right? The source type, is it a moment tensor source or is it a body force source or whatever source it is, right? Is it a point source or is it sort of finite source, that kind of thing. But here it's a lot simpler. You have just the longitude and latitude, right? And you don't even have a column for depths because all those sources are actually virtual sources. It's an impulse located at the receiver location. So the depth is going to be 0 for all those sources. So the code is actually intelligent enough to actually tell what kind of format it is, right? If it's just got like these two columns, it's going to treat the two columns as the longitude and latitude for each of the source that's listed in this particular text file, right? Here it's just longitude and latitude in degrees. So there's also a utility code called CRT. Called CRT, coordinate transform. Right? So if you don't have longitude latitude, but instead you have UTM, then this CRT code is gonna read the projection string, set up the projections, and then do the conversion between UTM and coordinates, longitude and latitude. So Do I have a CRT code? Yeah, CRT. That's the CRT code, right? It's a very simple code, but it's gonna require like a 1, 2, 3, 4, 4 inputs, right? The first is the inversion control file, right? The second one is the input file name, the output file name, and then a transform flag is gonna be if it's a 0, then it's gonna convert UTM to longitude latitude in terms of degrees, and it must be in this order, right? So the first column is gonna be longitude, the second column is gonna be latitude, and then if it's not 0, if it's anything else, then it's gonna convert longitude latitude to UTM, right? So in order to actually use this particular code, all I have to do is to actually um, just it's a CRT, right? And then that's the first input, right? And then the second input is supposed to be uh, uh, receivers dot UTM, right? And then the output file, let's sr info receivers dot deg1 because I have a file already. And then the transformation, um, the direction of the transfer is from UTM to longitude latitude, right? UTM to longitude, that's the flag has to be 0, right? And then it's gonna read the projection string. It's gonna read the projection string, and then do the conversion. And then the output file is gonna be inside of the sr info subdirectory of the job directory. So sr info, right? Sr info, and then I can do a diff, right? See if these two files actually has any kind of difference. Oh, somehow it's kind of different. So pretty much every line is actually different. So let me see what's actually happening here. Uh, it's just because the format, it's a scientific sort of notation format, but the numbers are actually identical, right? Maybe slightly different. I don't exactly remember how I actually got this particular file. It's probably created by MATLAB or something. Yeah, but that's how you can actually create convert UTM 2 degrees to longitude latitude and vice versa, right? Um, so once you've got that particular source list, the next thing that you have to do is to actually run a code called WPS. Again, I have actually written a shell script for calling WPS, right? This WPS command, this binary only takes like one input. That's the command line input. Lots of the binaries only takes like this one input, and then it's gonna bootstrap itself to find all the information that's needed in order to actually do the rest of the calculations. And that's so WPS means write point source, right? So it's gonna create all the directories inside of the FWF subdirectory, right? So by default, it's gonna just use the line number inside of the source list. So the first line is gonna be named as P001. The second line is gonna be named as P002, right? And then I have like 400 lines, 400 sources in that receiver.deg file. So I've got like 400 subdirectories. And then inside of each of the directories, it's gonna create a particular file that's called p003.in, and this is gonna be the file that's gonna be read by SW4, right? So you can sort of take a look at this particular input file. So in this kind of ambient noise in tomography, all the receivers are acting both as receivers and also as virtual sources. So for the source line, so here that's the source line, right? The source line is just one of the receivers, except that it's got a body force mechanism, right? And then it's got a source time function, right? So basically that's the virtual source, right? But it's also one of the receivers. And then all the rest of the receivers are listed here as a receiver line with the correct longitude, latitude, and also depth. Now it's displacement, right? Because we specified so in the inversion control file, and then by default it's gonna write this so-called USGS format. Right, it's a text file, it's an ASCII file, and then it's gonna do a screen printout every 10th time step. Right, and this screen dump is gonna go into the job script output file. Right, and then that's for creating this particular input file that's going to be read by SW4, right? Um, yeah, that's WPS, right? That's WPS. So after WPS is run, we are going to have the correct forward simulation directories, right? We are going to have all the directories and also the input file inside of it. But there's one more thing that we need to do in order to actually set up the directories correctly for running the forward simulations using SW4, and that's inside of this piece of code. It's so this code is called pre. Pre means pre-simulation. So after you have finished running this code, the directories should be ready for running forward simulations using either AWP or SW4, right? So what this code is going to do is that it's going to check the existence of the directories and also the input source files, right? Um, So by default, if you do not specify a particular source receiver ID, then it's going to be P followed by a line number, and then with the line number is pretty much just the receiver or source ID, basically. P followed by the line number, and then the line number is going to be filled up. It's going to has a constant width. For now, it's like 3 characters, right? And then if the total line number doesn't reach like 3 characters, 3 digits, then it's going to be filled up with zeros, and that's going to be the source receiver ID, and then it's going to check the existence of the source file. If it doesn't exist, then it's going to print out the missing source file, and then it's asking you to create the source file, and then it's going to so for every directory for running SW4, you must have a copy of the inversion control file. And you don't have to create a hard copy. All you have to do is to actually create a soft link towards that particular inversion control file, right? And this soft link is actually created inside of this pre. So if we still look at, maybe I should look at a directory with less content, right? This is one of the directories with less content. So you sort of see the control file, right? It's a link to the control file, basically, right? And then the directory is actually complete. You have to sort of create the job scripts called run.sh, and then just submit all the jobs. And this is on Cheyenne. It's a big computer, and I have to run lots of simulations, right? It's not just like one simulation is done. So because I have like 400 simulations, 391 actually, 391 simulations I have to run. So I do have to actually create the job scripts automatically. I cannot actually try to go into every subdirectory and then manually write the job script. So what I did was to actually create a template job script called run sw4.sh. So this is I'm using bash as my shell. So and then this template is gonna have the test as a job name, and then the script output. So for all those runs, it's gonna use like a 2 nodes and 36 CPUs or cores on each of the node. So that's like 72 CPU cores. And then the MPI processor is also MPI processor. Okay, so that's MPI processor per CPU core per node, I think. So that's also 72. So 72. Uh, I'm gonna use 72 CPU cores or 72 MPI processes to run SW4, right? And then this is a job template, right? And then I've got a Python script for creating the jobs from a template, and then that's called jobgin.py, right? And this this Python script is gonna take whatever job template that I'm actually using, and then the source receiver list, right? And then the run directory, that's the FWF subdirectory, and then it's gonna write out a qsub all. That's a shell script for submitting those 400 job scripts, right? In just a one shell script, and then it's gonna loop through every line inside of that source receiver list, and then replace the text test with the job ID with the source receiver ID, and then place that new job script into the run directory, and then write a line of qsub of that particular job script into the qsub all output file, right? So this is the Python script for creating all the job scripts, and then for SW4 I have a shell script for calling that Python script. So if I look at that, right, it's basically calling this Python script with this run sw4.sh as a template, and then source receiver list dat. So what is this thing? But that's the source receiver list, right? So that's the list of sources that I want to run simulations on, right? So maybe not every source. Let me just take a look at it. Source list.dat. So it's a floating point numbers, but it's actually integers, right? It's integers 1, 2, 3, 5. So skipped 4, 6, 7, 8, 9, 10, 8, 9, 10, 11, right? So how many lines do I have? 391. So I have to run for the SW4 simulations for 391 sources among the 400 sources. And then this is actually the source list, right? It's just the source ID that I want to run for simulations on. And then that's the directory for storing all the forward wave fields. And the job scripts are going to be placed inside of the subdirectories for each of the source inside of this FWF subdirectory. And then that's qsub sw4.sh is going to be the shell script I have to execute in order to actually submit all those 391 jobs. So after I finish running this particular script, shell script, I should have all the run.sh inside of my source directories inside of the FWF directory, and then I should have this particular file, right? So if I do a head qsub sw4.sh, it's gonna do a qsub on every run.sh, every job script inside of the job directory, and then I should have like a 391 lines for the qsub sw4, right? So then all I have to do is to actually run this qsub sw4.sh job script, right? This shell script to submit the 391 jobs. Xiaoyan is a big computer, so 391 jobs takes like a very short amount of time to actually run, because each job takes only like 2 nodes, right? So they almost run immediately, and then the simulation completes in about 3 minutes, 3 minutes of war time, right? Um, it's a substantial improvement in terms of speed compared with the DG code. The DG takes how long? The DG takes uh, like 20 minutes, right? 20 minutes on about on more than 2,000 cores. This is 73 minutes on 72 cores for the same kind of simulation. The parameters are pretty much identical, so that's like a huge improvements in terms of uh, efficiency, right? Uh, and then after SW4 finishes running, I'm gonna have this kind of outputs, right? So all those .txt files are synthetic seismograms, right? And then all those WF followed by the 6 digits after the WF is the process ID or partition ID. Pretty much every process writes its own output wave views, stream views, the synthetic seismograms are the so-called USGS format, right? So maybe I should go into one of the directories that has lots of stuff inside of it. Oh, that's P004. It's got lots of stuff in it, right? So these are stream views. Those are binary data. So people cannot read it, but the codes can. And then these are text files, a synthetic seismogram. So maybe I should just do a cat, right? The simulation, the first column is going to be time, right? So it goes up to like 1 second. Um, that's the simulation time that we specified inside of the inversion control file imv.in, right? And then that's the displacement in the x direction, displacement in the y and z directions. And then at the beginning of the file, you've got a bunch of headers. Right? Doing some kind of explanation about the format. This is called the USGS format, right? So the code can read this particular format as synthetic seismogram, and then we can run codes to make misfit measurements on this kind of synthetic seismograms, on this kind of data format. Right. So that's the two primary outputs, right? And then there are some optional outputs. For example, this kind of test.cycle equals to this thing is for two-dimensional cross-section views and map views of various material properties. For example, VP, VS density, right? And then longitude, latitude, and topography, that kind of thing. And then there are a bunch of other files, .wing and .wpk. Those files were created later on once we have picked the time window for doing the misfit measurements. And then WPKs are the wave field perturbation kernel that's going to be used for computing the data sensitivity kernels by the kernel code. And then for this binary data format, right? This kind of binary data format, how it's actually stored, right? How it's actually stored. So I'm showing you the output, right? I'm showing you all the outputs generated by SW4. But in order to actually get all those outputs, you have to actually do like two. You have to do two runs. That's going to generate both the mesh information and also the model parameter information for every recording grid, right? So the correct sequence for running SW4 is like this. So here. That's the opening up the soft link inside of this running job directory to my control file. The right info, right? That's the first line. So what I have to do is to actually put 1 here for the first run of SW4, right? That's the first run. And this run is going to end up very quickly. It's not going to take like 3 minutes. It's going to take like a few seconds, right? And then it's going to exit, right? It's going to do an MPI abort. So you're going to see error messages inside of the job script output. It's going to tell you that the job quitted. Right? But it's okay because the purpose for this particular run is to actually create the mesh information inside of the velocity model directory. So when write info equals to 1, it's gonna create a bunch of this kind of file, .info file, right? And then if you look at the .info file, it basically specifies the grid range for every subgrid for that particular partition for MPI of MPI process, right? So we've got like two subgrids, right? Grid 0 and grid 1. Grid 0 actually stays at bottom. It's the grid 0 is always the lowermost subgrid, and then grid 1 is the subgrid on top of grid 0 and then goes up. So here we have like two subgrids. If you have topography, two subgrids is like the minimal because you must have a curvilinear grid or curvilinear subgrid to account for topography, right? And then a Cartesian grid for at the bottom, right? So at least you have two subgrids. And then for partition 0, 0, 0, 0, 0, 0, x goes from 1 to 34, y goes from 1 to 31, and z goes from 1 to 16 for the first grid, and z 1 to 51 for the first for the second grid, right? And the partition is different from AWP. AWP allows you to partition along x, y, z three directions, right? But here it only allows you to partition in the x and y direction. So every partition, every process has to do all the different depths across all the different grids, subgrids, right? So if you look at the second input, that's gonna have a different x range, right? Oh no, different y range now, right? Different y range, but the x and z range is kind of the same. And you are supposed to have how many files? 72 files, because I specify 72 partitions or processes, right? And then you are supposed to have this kind of z file, and this z file is actually storing the x, y, z coordinates in terms of meters for every grid point inside of the curvilinear grid, right? And these files are going to be useful later on once we want to compute the volume for each of the for each of the cell, right? That's going to be used for when computing the kernels. And those files are also useful when we are trying to actually search for a particular the location of a particular point, the grid number, right? Inside of the entire mesh, right? Because inside of the curvilinear grid, the z direction is not uniform. It actually varies depending upon the topography. And then it's going to generate one more file. That's this particular text file called grid.info, right? And this grid.info is going to record the bottom depth for every subgrid, the bottom depth. So for grid 0, the bottom depth is going to be 65 meter. And then for grid 1, the curvilinear grid, the bottom depth is going to be 50 meter, right? And then the grid spacing, the horizontal grid spacing in both subgrids, it's going to be 1 and 1 because we didn't actually do any kind of grid refinement. But SW4 allows you to do a grid refinement, right? So horizontal grid spacing is just going to be constant 1 meter, right? And then this is going to be what? I think this is a time step length, right? So the time inside of the SW4 time step length is actually computed based upon the velocity model and also the grid spacing. Yeah, I think it's yeah, I think that's the time step length, right? Delta t time step length, and then the actual projection string used by SW4, right? So SW4 also uses the PROJ4.4 to do its projections. And then the longitude and latitude of the origin, right? And then the azimuth of the positive x-axis. And that's pretty much all the information that's needed in order to describe the entire grid, right? And that's for write info equals to 1. That's for write info equals to 1. and then the, and then we have to sort of change run info to 2, and then do another run, right? And then this run is also gonna have a MPI abort as the end, right? So it's still, the job script is still gonna tell you error messages, but it's okay because this run is gonna create a the model output, right? So it's gonna create lots of those kind of files, MDL, this kind of thing, right? The model files are gonna be used, it's binary, but they are gonna be used for storing the material property, VPVS and density, at every so-called recording grid point, right? So those material properties are going to be needed in order to actually compute the kernels later on, right? The kernels has to read the material properties and then do its calculations. So what are the recording grid points, right? So there are random recording grid points and the uniform recording grid points. The uniform recording grid points are created by using this particular shell script. So if you look at this shell script, it's calling this binary URG called uniform recording grid, and then the only input file is inv.in. That's the control file, right? And then inside this inv.in, we have specified the skip, the number of grid points to skip in the x, y, and z directions for both subgrids, right? And x, and y, and z, right? And then the URG code is gonna take that information and decimate the simulation grid according to this kind of skip rate, right? So in the x and y direction, it's going to save every 5th grid point. So the grid spacing for the recording grid is going to be 5 meters in the 2 horizontal directions. And then in the z direction, it's going to save every grid point. So the grid spacing is going to still be 1 meter, right? And then the URG is going to use that information to actually create those text files called GRD-REC, right? If I do a head on this particular file, it's a text file, it's an ASCII file, it's not too long, right? At the beginning, it's going to show 2 numbers. That's the total number of recording grid points for that particular partition, for each of the subgrid. And it's stored in from top to bottom, actually. So this is going to be for grid 1. That's the curvilinear grid accounting for topography. That's the topmost grid, right? And then that's going to be grid 0, right? The total number of recording grid points for grid 0. That's going to be 735, right? And then it's just going to store the different coordinates for each of the subgrid. So you have like 4 integers. The first integer is going to be the grid ID. So it's again starting from the top, goes down to the bottom, and then the direction is the loop is that x is going to be the fastest direction, and the z is going to be the slowest direction, and the z direction is going to change from the shallowest to the deepest. So SW4 has a z coordinate that's pointing downwards as positive, right? So grid 1 is actually the shallowest, right? And then it's going to increase, right? But its z direction is going to increase the slowest, but x is going to be the fastest, right? And then now it's z equals to 2 now, right? And then it's gonna go on like that. And then once you have entered grid 0, the first column is going to change from 1 to 0, right? So that's the so-called recording grid. And then if you look at the content of the MDL files, they are binary. They are not readable by human beings, but the ordering of the material properties is exactly following the same ordering as the recording grid format, right? It's going to start from the the top, and then goes down to larger depths, and then from grid 1 to grid 0, and then for every grid point is gonna store 3 doubles. That's VPVS identity, right? 3 doubles for every grid points. For every recording grid point, basically. For every recording grid point, we have like 3 doubles. And that's writing info equals to 2, right? And then after you have finished writing info to 2, you can change it to like 3, right? So writing info equals to 1 and 2 needs to be run only once. Only once. You don't have to run writing info for every shot or for every source. It doesn't have to be. But the writing info equals to 3 has to be run for every source in order to actually generate the wave field, to generate the strand fields, right? The grid info and material info doesn't actually change from source to source. If it's inside of the same simulation box, then it's independent of the source ID, right? So that's one of the things about the writing info, right? So once you have increased the writing info to 3, then you have to sort of go back to the jobs directory, right? Go back to the jobs. Did I do it right? And then run this shell script q sub sw4. Run this particular job script to submit the 391 jobs for all the sources that we're gonna use in our inversion, right? And then all the wave field output files. The wave field output files, like this kind of WF, these binary files. These binary files are stored in the same order as the material property files, right? So they are also following the exact same order as the recording grid file, right? The GRD REC file, those text files, it's starting from the top and then goes down to the depths, with the X being the fastest direction and the Z being the slowest direction, right? And at every recording grid point, it's gonna store 6 doubles. That's the strand fields, a strand tensor. It's gonna store the 6 components of the strand tensor at every recording grid point, with the ordering that's following some kind of order, right? It's basically the diagonal first, right? X, X, Y, Y, and Z, Z, and then it's following the so-called Voiger convention or something. VRGT notation, right? So it's gonna follow this kind of convention, XX, Y, Y, Z, Z, and then YZ, XZ, and then XY. That's sort of the convention for storing the different components of the strand tensor at every recording grid point, right? So and then the kernel code are gonna use those wave field outputs to actually compute all the kernels, right? But maybe this video is kind of long enough. Let's do the rest of the work in the next video.